Welcome back to our video series in mathematics. We have so far discussed various properties of multivariate functions. We have discussed continuity, we have discussed differentiability, and now we're going to take this to the applications. In particular, we like to find minima, maxima, and all kinds of optima of multivariate functions. So our next section will be Section 14, multivariate optimization. And we will start with the question of how to characterize local minima and local maxima of multivariate functions. You will remember in the univariate case, for functions defined on the real line, that was usually done by setting or finding the points where the derivative was 0, and then characterizing these points, whether they were minima or maxima, through either looking at the first derivative and its behavior or looking at the sign of the second derivative. And we try to find something similar in the multivariate case here. So that is the first part of chapter 14. That is the characterization of local optima. Now, before we characterize local optima, before we find criteria for what a local optimum could be, we first have to define precisely what we mean by a local optimum. So we'll do just that. That is the first definition of that section. As usual, we let X be an open set in R to the n. We consider a function f defined on X that maps to the reals. And then we'll introduce the following terminology. First, we'll say a point is called a local minimum if there is a neighborhood around that point such that there is no function value within that neighborhood that is less than the function value at that minimum. Okay, so a point x star in X is called a sometimes strict local minimizer of f if there is a delta neighborhood around that point, of course. So n delta x star of x star such that the following holds. So we want f of x star to be less or equal to every other possible function value f of x for all x in that neighborhood. And of course, we also have to make sure that x is actually in the domain of the function. So we'll take capital X intersected with that neighborhood n delta of x star. The strict part here, that of course holds if and only if we have strict inequality without the possibility of the function values being equal. Okay, so that's a minimizer. The definition of a maximizer is analogous to that one, so that's part 2. A point x star in capital X is called a, again, possibly strict local maximizer of f if there is a delta neighborhood and delta of x star such that, well, for a maximizer we need f of x star to be greater or equal to f of x for all x in X intersected with that neighborhood. In analogy to these local definitions, we can of course also define what a global minimizer or maximizer is. So that's point 3, and we do both minima and maxima in one take now. So a point x star is called a possibly strict global maximizer or minimizer of f if, well, the following holds. For the maximizer, we want f of x star to be greater or equal to f of x. For the minimizer, we want f of x star to be less or equal to f of x. And again, these have to hold for all x in X. So this time we don't need a neighborhood. We need that to hold for all values of x in X, respectively. And again, if strict inequality holds, then we have a strict global maximum or a strict global minimum. Okay, point 4. Although we often use these interchangeably, we've defined the x values to be the minimizers or maximizers. So if you want to stress that we're talking about the function values, then we are talking about the minima or maxima of the function. And just to note that these both minimizer and minimum are often used interchangeably, and the same works for maximizer and maximum. Okay, so the respective function values are called a possibly strict local or global minimum or maximum of the function f. And finally, part 5. If we do not want to distinguish between minimum and maximum, then we often refer to these points as extremum or optimum. So a local or global, strict or not, minimum or maximum is also referred to as extremum or optimum of the function f. Okay, so that's the definition. The next thing we have to do is find out how this is related to differentiability. And if there is a condition like in one-dimensional theory that the derivative is 0, the gradient is 0, or whatever other value it might have to take. So let's investigate the situation of a local minimizer in the interior of a set X first. So let's say X star is a local minimizer in the interior of a set. We want the interior because we want to be able to move in every direction. And we want it to be differentiable. The function wants to be differentiable at that point. Okay, so we can move in every direction. And we want f to be differentiable. So f x to r is differentiable at that point x star. Then what we can do, we can move from our current point x star in the direction of the gradient or the negative gradient. Make a little step in that direction, and let's call that a new point x. So we can move from x star to a new point, and the new point x will be defined as x star minus some epsilon times the gradient of f at x star for a sufficiently small epsilon. And what we mean is by sufficiently small is it needs to guarantee that the new x is still contained in the set X, of course. Yeah, so that this move is actually permissible. Okay, so we move to that new point. We move a little in the direction of the negative gradient. What happens to the function value? We know that f is differentiable. So we know that we can approximate f by a linear function. So f of x is f of x star plus the gradient of f at x star transposed times x minus x star plus the remainder of x minus x star, and that remainder goes to 0 more quickly than x goes to x star. So what does that mean? Well, if we use our definition of x here, then we get the function value at the new point is the same as that at the old point, plus the gradient transposed, and now x minus x star. That actually means that this part here vanishes, so we're left with that second part here. And that means we have minus epsilon times the gradient of f at x star in here. And again, plus that remainder. Okay, now what happens here is, well, this is f of x star. we can take out the minus epsilon, and then we have the gradient of f at x star transpose times that gradient. So that's the same thing as the norm of that gradient squared, and then plus the remainder. So what happens if we move close enough to the point x star so that this remainder is very, very small? That means we can take a small step away from x star in that direction and effectively reduce the function value. So the new function value is f of x star minus epsilon times something positive. And remember that x star was a minimizer, so there needs to be a neighborhood around x star where we cannot reduce the function value. But what that says is, with a very small step away from x star, it will be possible to reduce the function value. That cannot be true, and that means the only way out of this is that this norm here, and therefore the gradient itself, that needs to be 0. And that's precisely the condition that we wanted. Yeah, so that's what we get in the multivariate case as well. So let's make a quick note of that. As this remainder here goes to 0, as x goes to x star, that means that we can take a small step away from x star in direction minus gradient f of x star to reduce the function value below f of x star. Now this obviously cannot be true. X star is a minimizer, therefore that cannot be true. And that means the only way out of this is this norm here of the gradient of f at x star, that must be 0. And of course that means, well, if the norm of a vector is 0, then the vector itself is 0. That was one of the key properties of a norm that we discussed in the first semester. Okay, and that's basically what we wanted to prove. And of course we can make the same argument for a maximizer as well. Yeah? So let's just quickly note this. An analogous argument can be made if x star is a maximizer. So we have effectively proven the following theorem, and that's the main result of this video. Let x be a subset of R to the n, open. Let x star be an x, and let f be a function from x to R that is differentiable at x star. And now if x star is a local optimum of f, then we have shown that the gradient needs to be the 0 vector. If x star is a local optimum of f, then the gradient of f at x star is the zero vector. And this theorems of that kind are known as first order conditions for local optimality, meaning that they use the first derivative, nothing beyond that. That's why they call it first order conditions. And it's a necessary condition. That means the reverse is not necessarily true. We have already seen examples where the gradient was zero, but we did not have a local optimizer. You will remember functions where we had a saddle point. For example, a function like this specific function here. You remember how that we plotted that before. And you can see the origin is a saddle point, so that's neither a maximum nor a minimum, but the gradient at that point is still zero. Okay, so the theorem is necessary. If we have a local optimum, then necessarily the gradient is zero, but the reverse is not necessarily true. If the gradient is zero, that does not mean we have a local optimum yet. It can still be a saddle point. And in one of the next videos, we'll try and see if we can find conditions that guarantee that a point is actually a local optimum. Let's just make a quick note of that one here. So that theorem is a necessary first order condition for optimality. Okay, finally, as these points here with gradient zero play such an important role, we just give them a name. So that's the final definition of this video here. Let x be in R to the n open. Let f be a function defined on x mapping to R differentiable. And then number one, a point with zero gradient is called a stationary point. So point x star in x with gradient of f at x star equals the zero vector is called stationary point of f. And second, we've already used that term. If we have a stationary point that is not a local optimizer, then it is called a saddle point. So if x star in x is a stationary point, but not a local optimizer, then x star is called a saddle point. Okay, this concludes this first take at conditions for optima. Next, we're going to have a look at second order conditions that will tell us a little more about whether a stationary point is actually an optimum and whether it is a local minimum or a local maximum.